4 human beings are now confined in a capsule just 5 meters wide, traveling at thousands of kilometers per hour toward the absolute void of deep space. The silence of the Florida night was broken by a roar the Earth hadn't heard in over 5 decades, marking the exact moment we ceased being a species confined to the ground and reclaimed our place among the stars. What you are witnessing is not just a rocket launch, but the beginning of the Artemis II mission, the first real step toward establishing a permanent presence on another world. This event represents the first time since 1972 that humanity has sent people beyond low Earth orbit, challenging limits many believed had been forgotten. Aboard the Orion capsule, 4 explorers bear the responsibility of testing every life support system and every orbital maneuver necessary to ensure that this time our stay on the moon is not just a quick visit. The vehicle carrying them is propelled by the SLS, the most powerful launch system ever built, a 98-meter-high structure that consumes 6 tons of fuel every second to break through Earth's gravity. However, behind the technical grandeur and epic ignition images lies a set of calculated risks and hidden structural flaws that make this journey far more dangerous than official statements suggest. Understanding what is at stake requires looking beyond the visual spectacle and delving into the raw engineering that separates historic success from an interplanetary scale disaster. The technology that took us to the moon in the last century was less powerful than the processor in a modern digital watch, but the dangers of today are new and invisible. To understand the magnitude of what is happening now, we need to dissect the hardware involved in this billion-dollar undertaking and the reasons why it took us so long to return. The Artemis II mission is not simply a repeat of the Apollo program. It utilizes a completely different architecture, focused on sustainability and long-term exploration. The SLS rocket, with its orange core stage and 2 solid fuel boosters, generates thrust equivalent to 14 large commercial airplanes, providing the energy needed to put Orion on a free return trajectory. This orbital path is a gravitational insurance policy. If something fails in the main engines, the moon's own gravity should pull the capsule back home. But this plan depends on absolute mathematical precision and the integrity of components that have faced serious problems in previous tests. Many people question how the SLS rocket actually works and whether it is capable of withstanding the extreme thermal pressures during ascent. The answer lies in the combination of the 4 RS-25 engines inherited from the space shuttle era with the cutting-edge technology of the temporary cryogenic stage. Every detail, from the 5-centimeter insulation foam to the coupling systems, was designed to protect the crew in an environment where any mistake is fatal. Beneath the metallic surface of Orion lies a complex artificial ecosystem designed to keep 4 adults alive in an environment that attempts to kill them with every second of exposure. The Orion capsule's life support system is the beating heart of this mission, responsible for regulating pressure, oxygen, and carbon dioxide removal. Unlike space stations orbiting near Earth, Orion must cope with direct cosmic radiation and the complete absence of rapid external assistance. The engineering behind waste management and the efficient use of internal space is what allows the crew to survive for 10 days in a volume comparable to that of a utility vehicle. There's a technical curiosity that has few details: the logistics of the routine. Living in a 5-meter space demands extreme psychological and physical discipline, where every gram of cargo and every liter of water is monitored by redundant automated systems. The public frequently asks how astronauts manage to maintain hygiene and sanity in such rigorous confinement while traversing the Van Allen belts, zones of intense radiation surrounding our planet. Imagine being locked in a small room with no windows open, knowing that the only thing protecting you from instant death by radiation or vacuum is a layer of composite material and the technical judgment of thousands of engineers on the ground. This tension is constant. During the Trans-Lunar Injection phase, the engines must fire at the exact moment to ensure the capsule reaches the necessary speed without disintegrating or being lost in space. The SLS uses liquid hydrogen and liquid oxygen stored in colossal 2 million-liter tanks, a highly volatile mixture that requires perfect thermal insulation. During ascent, the vibration is so intense that it can compromise the integrity of delicate sensors. What differentiates Artemis II from any simulation is the human presence. Now, decisions are not just algorithms, but reactions under extreme pressure. The capsule also needs to face micrometeorites traveling at hyperbolic speeds, capable of piercing conventional shielding. Protection against these impacts and thermal management which needs to balance the heat of the sun on one side and the cold of absolute zero on the other, are the pillars that support the viability of the mission. Although the launch was a visual success, there is a critical component that silently failed in the previous mission and is now NASA's biggest concern. The Orion spacecraft's heat shield is the most closely watched piece of hardware by experts at the moment. During the Artemis I re-entry, unexpected wear and cracks were observed in the ablative material that shouldn't be there. Modifications were made for Artemis II, but the real test will only happen when the crew hits Earth's atmosphere at almost 40,000 kilometers per hour. Furthermore, there's the mystery of the far side of the moon. When the capsule passes behind our natural satellite, the crew will face the engineering of silence, 45 minutes of total isolation without any communication with Earth. During this period, the astronauts will be on their own, relying exclusively on internal systems to perform critical orbital maneuvers that will determine whether they return or remain trapped in perpetual orbit. All this technological preparation seems flawless, but there is a design flaw in the re-entry system that was deliberately ignored in the initial public reports. The data collected suggests that atmospheric turbulence could affect Orion's stability in a way that onboard computers may not be able to correct in time. If the heat shield doesn't behave exactly as predicted, the capsule risks becoming a funeral pyre before even touching the ocean waters. The crew's safety depends on a series of cascading events that need to occur with millisecond precision to avoid the worst possible scenario. The delivery of this phase of the mission focuses on validating the risks of Artemis II that many prefer not to discuss. We are talking about a vehicle that, despite being modern, carries the weight of delays and budget cuts that force difficult technical decisions. The integrity of the solid fuel boosters and the reliability of the RS-25 engines are tested to the limit in each phase of the flight. The central objective is to prove that the Orion capsule can sustain human life beyond the protection of Earth's magnetic field, facing sudden solar storms and unforeseen mechanical failures. The previously mentioned free return trajectory is our last line of defense, ensuring that orbital physics works in favor of survival, even if the main propulsion is lost. Understanding these risks is essential to appreciating the courage of the 4 astronauts who accepted the challenge of being the first to return to deep space. If you want to understand how humanity is facing these invisible dangers and want to follow every technical detail of this historic journey, sign up now and turn on notifications so you don't miss any updates on the fate of the Artemis II. Following this mission is witnessing history being written in real time. Your participation in the comments helps build a community of enthusiasts who seek the scientific rigor behind NASA's beautiful images. We want to know your opinion on the risks we've discussed here and whether you believe we are truly ready for this monumental leap. The success of Artemis II will determine the timeline for the next crewed landing, but a secret about the true costs of the SLS could change everything. We conclude this initial analysis with the certainty that the mission is a technological milestone, but also a reminder of our fragility. Every system, from the fuel tanks to the navigation computers, was pushed to its limits. What we discovered about the effectiveness of the rocket and capsule will serve as a basis for all future expeditions to Mars and beyond. However, the economic and technical viability of the Artemis program remains an intense debate behind the scenes at space agencies. We examined the raw power of the launch, but the real thesis of this mission is not about the rocket, but about a miscalculation in the trajectory that could change the crew's fate. What happens if Orion doesn't reach the exact velocity for Trans-Lunar Injection? The answer to this question reveals the darker and more dangerous side of modern orbital mechanics, something we will explore in detail below. A millimeter error in calculating the Trans-Lunar Injection trajectory would not only divert Orion from its destination, but could turn it into an eternal, silent satellite wandering through the solar system. For the mission to succeed, the upper stage engine, known as ICPS, needs to fire with absolute precision to overcome the final barrier of Earth's gravity. This critical component uses liquid hydrogen to generate the necessary acceleration that puts the capsule on a free return trajectory. This orbital engineering concept is the central safety thesis of the mission. The spacecraft is launched on a path that uses the moon's own gravity to whip it back to Earth. If the engines fail after this firing, physics becomes the autopilot, theoretically ensuring that the crew is not stranded in the void. The SLS rocket, which cost billions of dollars to develop, was structured around this premise of raw power coupled with passive safety. Its 2 solid fuel boosters, which now display the 250-year US emblem, provide the devastating initial thrust, while the Boeing-manufactured core stage maintains stability until the edge of the atmosphere. The complexity of coordinating these systems inherited from the space shuttle era with new navigation technologies is what defines the engineering of this decade. Many experts question whether the astronomical cost of the SLS is justified, but the technical reality is that no other current vehicle has the necessary safety certification to launch humans with such a high degree of redundancy into deep space. The secret to survival on this journey lies not only in the rocket's power, but in the hidden intelligence within the European service module attached to the capsule. This module, provided by the European Space Agency, is the true cruise engine of Orion, providing propulsion, electricity, and thermal control during the 10-day journey. Without it, the capsule would be just an inert shell without air or power. The electrical system is powered by 4 X-shaped solar panels, which need to be constantly oriented to capture maximum solar radiation while the spacecraft rotates. A common question from the public is how the SLS manages to maintain the correct direction during such intense fuel burn. The answer lies in the thrust vectoring systems of the RS-25 engines, which can tilt slightly to compensate for any variation in weight or atmospheric pressure. The fundamental thesis here is international integration. NASA provides the launch force and the command capsule, while Europe ensures the vital resources for staying in space. This collaboration reduces single points of failure, creating a system where each component has an independent backup. It is this architecture that allows the Artemis II mission to be classified as the safest manned flight ever planned, despite the extreme distance and radiation risks. As Orion moves away from Earth's magnetic protection, the crew faces the unseen danger of solar particles that can fry sensitive electronic components in seconds. The capsule's shielding engineering was designed to act as a protective cage against space weather events. However, closer technical analysis reveals that the greatest barrier is not only physical, but biological. Keeping Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen healthy requires rigorous control of the life support system. The public frequently asks whether oxygen is recycled or carried in tanks. In Orion, the system is hybrid, utilizing carbon dioxide filtration technologies that were tested on the International Space Station but adapted for the capsule's reduced volume. The internal space is optimized so that every centimeter has a dual function: supply storage and radiation protection. During the traversal of the Van Allen belts, the spacecraft's orientation is altered so that the denser service module faces the direction of the highest particle intensity, serving as an additional shield for the astronauts. Unlike in science fiction movies, there is no artificial gravity or spacious corridors. The reality is a metallic confinement where the constant sound of fans is the only guarantee that air is circulating and you are still alive. This technical claustrophobia is compensated for by the view through Orion's windows, which allow the crew to perform optical navigation should the radar systems fail. The precision required for the rendezvous with the Moon is such that any minimal gas leak could catastrophically alter the orbit. The SLS needs to place the spacecraft in a window only a few kilometers wide in space for the Trans-Lunar Injection to work. The fuel used, liquid hydrogen cooled to cryogenic temperatures, is extremely difficult to handle, which explains the numerous delays and cancellations of previous launches. If a sensor detects a pressure variation in the ICPS tanks, the mission can be aborted even seconds before the final burn. The thesis that we are ready depends on the reliability of this data flowing in real time to the computers in Houston. The free return trajectory seems like the perfect plan, but it hides a physical limitation that prevents any rescue attempt if the capsule suffers structural damage. Once the Trans-Lunar Injection burn is complete, Orion's speed is so high that no other spacecraft currently available could reach it for a deep space rescue mission. The public questions what would happen if the heat shield were to suffer a micrometeorite impact during the outbound journey. The technical truth is that the crew would only discover the extent of the damage upon re-entry, making each phase of life a test of faith in the integrity of the composite materials. Orion's outer shielding uses a special resin that carbonizes to dissipate heat, but its effectiveness against high-speed debris is based on statistical models. Even with all the power of the SLS, there is a specific point in lunar orbit where communication will be cut off and the crew will be completely blind, relying on a computer code that has never been tested on humans. This radio blackout is not merely a technical silence, it is the moment when NASA's safety thesis faces its greatest paradox. If the automated system fails, while the spacecraft is behind the moon, there will be no possible human intervention in time to prevent the deviation. The completion of this technical phase confirms that the SLS has fulfilled its primary function, but the real challenge now is the thermal stability of the Orion capsule in a vacuum. Internal temperature regulation is one of the biggest questions from the public. How to keep the interior habitable if one side of the spacecraft reaches hundreds of degrees under the sun and the other plunges into absolute cold. The engineering solution is passive grilling, where the capsule rotates slowly on its axis to distribute heat evenly. This rotational movement needs to be coordinated with the pointing of the high-gain antennas to ensure a constant data flow with Earth's deep space network. The thesis that current technology is superior to Apollo's is proven here, with systems that monitor millions of parameters per second, something impossible in the 1960s. The reliability of Lockheed Martin's flight software is what sustains the confidence that Orion will be able to make the necessary course corrections after the lunar encounter. If this level of technical detail about how space missions actually work is what you're looking for, leave a like now so the algorithm understands that real science deserves to be shared. Your interaction is what allows us to continue producing documentaries with this level of documentary rigor. Comment below whether you trust passive orbital physics or active propulsion systems. More to bring these four heroes back home. We are reading every contribution to refine our next blocks of technical analysis. Everything we've discussed about the perfection of the SLS, and Orion ignores a human factor that could compromise the mission long before we reach the moon. The integration of the crew with the spacecraft's digital systems requires a response time that physical fatigue and radiation stress can degrade. Tests conducted in Houston show that cognitive performance decreases significantly after the third day in deep space. The thesis that automation solves everything will be put to the test when the first real alarm sounds in the middle of the orbital silence. The efficiency of the cabin design, focused on ergonomics by Victor Glover and his colleagues, is the last barrier against human error. We believe that the thesis of absolute safety is unshakable, but data from the Artemis II mission revealed something disturbing about the behavior of oxygen in the tanks that NASA has not yet fully explained. If this anomaly were to repeat itself with humans on board, the life support system could enter a catastrophic failure cycle in less than 48 hours. What the engineers discovered in the wreckage of the previous mission calls into question all the stability we have presented so far. If the anomaly detected in the oxygen tanks of the previous mission is repeated with humans on board, the life support system could collapse in less than 48 hours. The confidence placed in the engineering of the SLS and Orion now faces scrutiny from data that NASA hesitates to fully detail. Although the launch was a spectacle of power, the reality in deep space is unforgiving and reveals that not even the billion-dollar investment can predict the behavior of materials under constant radiation. A latent doubt among enthusiasts is whether the heat shield, which showed unexpected wear on Artemis I, is truly ready to protect Reed Wiseman and his team during the violent re-entry at 40,000 kilometers per hour. The ablative AV coat material, designed to burn and dissipate heat, released larger fragments than predicted in previous tests, creating a scenario where the integrity of the capsule becomes a statistical gamble. Furthermore, the operational cost of each launch, estimated at over $4 billion, puts the program under political pressure that could force cuts in vital redundancy systems. The antithesis of space progress is the financial and technical fragility of a project that inherited components from the space shuttle era for a mission that demands 21st century technology. The rocket that takes us away from Earth is the same one that consumes the budget that should guarantee our safe stay there. The danger lies not only in the mechanics of the rocket, but in the fact that we are sending astronauts to a region where rescue is physically impossible. Unlike missions in low Earth orbit, where an evacuation to the International Space Station would take hours, on the lunar trajectory, time is measured in days of agony if something fails. The public frequently questions why we don't use backup spacecraft or quick docking systems for emergencies. The technical answer is disheartening. There is currently no other vehicle capable of reaching Orion in deep space. The European service module, although sophisticated, is the crew's only survival engine, and any leak in its helium valves would paralyze the spacecraft in a vacuum. The reliance on a single international propulsion system creates a critical failure point that contradicts NASA's own philosophy of redundancy. We are operating at the edge of what physics allows, with a margin of error that diminishes with every kilometer we move away from Earth's magnetic shield. While the world celebrates photos of Earth seen from a window, the crew battles the silent impact of solar radiation that Orion's filters cannot completely block. A deeper understanding of biological risks reveals that prolonged exposure to galactic cosmic rays can cause immediate neurological damage, affecting astronauts' reaction time in critical moments. A recurring question from the public is how they protect themselves during an unexpected solar storm. The improvised solution is to create a shelter inside the capsule using supplies and water tanks, but this reduces the living space to claustrophobic dimensions that degrade the crew's psychological well-being. Life support, already facing anomalies in its oxygen tanks, needs to work overtime to filter the excess moisture and heat generated by the physical stress of 4 confined people. Orion is a microcosm under constant attack from invisible particles that pass through aluminum and titanium as if they were paper. No one talks about the smell of ozone and accumulated sweat, or about how the sound of a simple screw vibrating can sound like a death sentence in the silence of the lunar vacuum. The psychology of confinement is the biggest source of curiosity at this stage. How will Victor Glover and Christina Koch maintain their focus when contact with Houston is interrupted by the mass of the moon? The public wants to know if there is a plan in case of a psychotic episode or a total communication failure. The truth is that the crew's autonomy is limited by software that can be hacked or suffer failures due to electromagnetic interference. The excess of automation, which should be an aid, becomes a barrier when astronauts need to take manual control of a system that doesn't respond. The complexity of Lockheed Martin's flight code is so vast that not even the crew knows all the possible error variables. The free return trajectory, presented as the greatest guarantee of safety, can become a trap if the spacecraft suffers a millimeter-level deviation during its passage through the dark side. If the approach speed is not corrected with absolute precision, the moon's gravity, instead of launching the capsule back to Earth, could hurl it into an elliptical solar orbit. The public questions whether the onboard fuel would be sufficient for an emergency correction in this scenario. Technical data shows that the margins are minimal. Any extra engine burn to correct the course sacrifices the energy needed for the atmospheric re-entry maneuver. We are walking on a gravitational tightrope where physics does not forgive hesitation. The mission's biggest secret isn't technical, but rather a discovery made by astrologers in recent images that suggests the moon may not be the dead desert NASA sold us. There are records of rhythmic lights and moving objects in the Shackleton crater that defy traditional geological explanations. If the Artemis II crew finds something that shouldn't be there, the radio silence protocol could last much longer than the planned 45 minutes. The delivery of this analysis on the hidden dangers forces us to question whether returning to the moon justifies the risk of losing 4 lives on a global network. The conclusion of this dialectical phase reveals the conflict between exploratory ambition and limited technical reality. The public wants to know if there is a secret plan in case the capsule becomes trapped in lunar orbit without sufficient oxygen for return. The sad truth is that the official protocol focuses on risk mitigation but offers no solutions for total isolation. The sustainability of the Artemis program depends on flawless success in this mission. Any error, however small, could mean the definitive end of manned exploration for another half-century. We are operating under pressure, where failure is not only a discarded option, but a ghost that walks the corridors of the control center in Houston. Your opinion on these risks is crucial to our community. Do you believe NASA is being transparent, or is there something more behind these technical problems? Subscribe and turn on notifications so you don't miss the summary where we'll reveal how humanity intends to overcome these paradoxes. Your engagement helps maintain this channel as a source of scientific rigor amidst so many unfounded theories. Comment on what you would do if you were in Jeremy Hansen's place facing the silence behind the moon. While we discuss technical glitches, an unpredictable external factor is approaching lunar orbit, and NASA has just issued a priority alert. An X-class solar event has been detected, and the shockwave is expected to hit Orion precisely at the moment of the Trans-Lunar Injection maneuver. The spacecraft's protection will be tested to the maximum limit even before they sight the first patch of lunar soil. The safety thesis we have built up to this point is about to be confronted by a force of nature that cannot be calculated. The problem is no longer just oxygen or the heat shield, but an unknown signal interference that has begun transmitting terrestrial coordinates from inside a lunar crater. Who or what is sending data to Orion from a supposedly uninhabited world? The answer to this mystery completely changes the purpose of this mission and will be the starting point of our next encounter. The mysterious coordinates coming from the Shackleton crater and the instability of the oxygen tanks force NASA to make an impossible decision between historical glory and the rescue of the crew. The resolution of this technological conflict requires a deep understanding of how human intelligence and automation need to merge to ensure survival in deep space. Although data from the previous mission raised concerns about the heat shield and oxygen, the practical reality of Artemis II demonstrates that redundancy lies not only in the machines, but also in the astronauts' adaptability. The balance between the raw power of the SLS and the subtlety of the European service module is what allows the mission to continue even under the threat of solar storms. The public questions whether current technology is truly superior to that of the 1960s. The answer lies in the real-time data processing capability that allows for debris avoidance and trajectory adjustments with millimeter precision. This fusion of international efforts transforms statistical risk into a controlled operation, where each anomaly is countered by a pre-programmed digital counterpart. The integration between command in Houston and Reed Wiseman's autonomy aboard Orion creates a safety net that the Apollo missions never dreamed of possessing, transforming the fragility of the previous thesis into a robustness tested under extreme pressure. Overcoming the technical challenges reveals that the true driving force of the mission is not just cryogenic fuel, but the global coordination of terrestrial infrastructure. For Orion to interpret signals from the lunar surface and maintain stable life support, a network of antennas distributed across Spain, Australia, and the United States works in unison. The public frequently asks about communication latency, how to solve a critical problem if the signal takes thousands of kilometers to travel. The solution is onboard autonomy, where the spacecraft's flight computer makes decisions in milliseconds to balance internal pressure and solar orientation. This decentralized architecture is what allows the mission to survive the radio blackout behind the moon, using inertia and predictive calculations to resurface at the exact location for re-entry. The looping curiosity about the anomalies in the Shackleton crater finds its answer in lunar geology, where deposits of ice and minerals can cause electromagnetic reflections interpreted as signals. This natural phenomenon, although it may seem like intelligent transmission, is actually proof that the moon possesses vital resources that justify the entire cost of the Artemis program. Further scientific data shows that the presence of hydrogen at the lunar poles is not just an academic curiosity, but the fuel station of the future for journeys to Mars. Addressing public concerns, many wonder if astronauts will descend to investigate. The reality is that this mission is a critical 10-day orbital test. The objective is to validate whether the life support system can maintain a stable atmosphere while the spacecraft performs the gravitational slingshot maneuver. The effectiveness of the AVCOAT heat shield, which has greatly concerned engineers, will be monitored by high-resolution external cameras during each phase of thermal stress, allowing adjustments to the spacecraft's orientation to avoid the excessive wear observed in the previous mission. Forget the mysterious lights. The real technical miracle is keeping 4 human beings alive in an aluminum bubble, where the only thing between them and absolute vacuum is a layer of epoxy resin. The logistics of survival reach their peak when we realize that every gram of cargo was calculated to balance the center of gravity during re-entry. The public wants to know how they sleep and eat in zero gravity for so long. Orion offers a more spacious environment than Apollo, allowing the crew to maintain hygiene and mental health through exercise protocols and video communication with their families. This emotional stability is the secret component that allows Victor Glover and Christina Koch to operate the manual docking systems with surgical precision should the automation fail upon return. The integration of the human element with robotic precision defines this new era of exploration. The combination of these technologies allows Orion not only to orbit the moon, but also to map future landing sites with a resolution never before seen by the human eye. Upon crossing the dark side, the spacecraft uses laser sensors to pierce the darkness and reveal the topography of regions that could support the first permanent bases. The thesis of fragility is replaced by evidence that we are ready to go further. Doubts about oxygen are resolved by the use of chemical recycling systems that reduce dependence on external tanks, an innovation that will be the basis for long-term colonization. The mission ceases to be just a test flight and becomes the foundation of an interplanetary economy. However, the maneuver of re-entering the Earth's atmosphere holds one last physical secret. The speed will be so high that the plasma around the spacecraft will create a heat barrier capable of vaporizing any material that is not perfectly aligned. If the wear and tear on the heat shield is just 1% greater than predicted, the Orion capsule could become a shooting star over the Pacific Ocean before even deploying its parachutes. The mission's success now depends on a variable that no one can control: the atomic resistance of a resin under temperatures of 5,000 degrees. The final delivery of this technical analysis shows that Artemis II is the perfect balance between the legacy of Apollo and the innovation of modern computing. The completion of this phase reaffirms that the risks, although real and documented, were mitigated by a global intelligence network. The public questions whether the investment is worthwhile in the face of Earth's problems. The answer lies in the advances in life support, water purification, and resilient materials that are now returning to use in terrestrial industry. The 10-day journey around the Moon validates the S.L.S. as the most powerful and reliable rocket ever built by humanity, silencing criticisms about its prolonged development. The cooperation between NASA, ESA, and CSA proves that deep space exploration is an endeavor that transcends national borders in pursuit of a common goal. If you've followed this technical journey so far and understand the importance of this moment in history, subscribe so you don't miss the final outcome of this mission. Your participation in the comments helps guide our future investigations into humanity's fate among the stars. Share this content with anyone who still thinks the return to the Moon is just a special effect. The science here is real and is happening now. With the crew poised for their final plunge into the atmosphere, one last radio signal is picked up, but this time it comes neither from the Moon nor from Earth. The frequency detected by Orion's sensors during the plasma phase indicates a transmission of unknown origin that appears to be synchronized with the astronauts' heartbeats. What should be just physics and heat becomes an event that challenges our understanding of biological reality in space. The rescue operation in the Pacific Ocean is already in place, but monitoring cameras show that the capsule descending may not contain exactly what was sent 10 days ago. Something changed inside the Orion during the silence of the dark side, and what emerges from those hatches will redefine what we call the human race. The end of this story is not the end, but the beginning of something far more disturbing. A split-second error in calculating the trajectory means not just a deviation from the route, but eternal silence for 4 explorers lost in the icy vastness of the vacuum. The precision required for Orion's safe return is so extreme that any variation in the Trans-Lunar Injection burn would transform the spacecraft into a ghost satellite of the Sun. Fortunately, the mission's physics were designed with an invisible safety net, the free return trajectory, which uses lunar gravity as a natural slingshot back home. We are facing a milestone that ends a 5-decade hiatus, connecting the legacy of Apollo 17 with the renewed ambition to establish a permanent human presence. Reed, Victor, Christina, and Jeremy are not just testing hardware. They embody the efforts of thousands of engineers from across the US and international partners. The success of this journey validates the heat shield, life support systems, and the viability of the European ESM under real-world stress conditions. By traversing the atmosphere at nearly 40,000 kilometers per hour, they bring with them the answers to the technical paradoxes we have discussed throughout this detailed analysis. Although a safe return may seem like the end of the line, the true panoramic view reveals that the ocean where the capsule will land is merely the edge of a new continent. The recovery of the capsule from the sea marks the end of 10 days of constant tension and uninterrupted monitoring by the teams in Houston. This moment of unification for the species is symbolized by a diverse crew that must balance extreme temperatures and psychological pressures to thrive in a hostile environment. Just as Orion manages the difference between the scorching sun and absolute zero, humanity seeks its own balance to move forward. The return of Artemis II should not be seen as an isolated event, but as the necessary proof of concept for the next steps. Overcoming the contradictions between the high costs of the S.L.S. and the need for deep exploration finds its point of reconciliation here. The technology that enabled this flight will serve as the foundation for the lunar laboratory and eventually for the first human footprints on the red sands of Mars. The total isolation behind the Moon raises a question that few dare to ask. What happens if the radio silence lasts longer than expected? During the 45 minutes that Orion passes by the far side of the Moon, communication with Earth is physically impossible due to the mass of our natural satellite. There are no dedicated relay satellites for this phase of the mission, leaving the crew in a state of absolute introspection and complete autonomy in the vacuum. This silence is the space where the new human identity is consolidated, far from any immediate support, depending exclusively on the robustness of the engineering we have previously presented. Every computing system and every fuel tank was pushed to its limits to ensure that these 4 individuals survived this interval of interplanetary solitude. Human fragility is confronted by the brute force of metal and code in an environment where micrometeorites and solar radiation are constant and silent threats. The technical grandeur fades when we realize that, to the universe, we are just a pale dot, desperately trying not to be erased by the darkness between worlds. In that moment of radio silence, the capsule transforms into a microcosm of Earth, where the origin or gender of the crew becomes irrelevant in the face of the need for survival. The unification of the species ceases to be a NASA marketing ploy and becomes a fundamental biological and technical necessity. Total isolation forces a reflection on our insignificance and, simultaneously, on our audacity to defy the laws of gravity with machines 98 meters tall. What these astronauts feel as they watch the Earth rise behind the lunar horizon is something that no telemetry can capture with absolute fidelity. It is the moment when science meets philosophy, and the cost of billions of dollars is justified by the expansion of human consciousness. Many ask why we haven't landed now since we are so close to the lunar surface, but the answer lies in strategic caution. Artemis II is not about the immediate destination, but about the people and systems that ensure a sustainable and safe return. Landing now would skip critical validation steps that could compromise the entire Artemis program and the future of Mars exploration. Trans-Lunar Injection and high-orbit maneuvers are the ultimate tests before we risk the first crewed landing of this century. The effectiveness of Orion's life support under intense radiation and the integrity of the heat shield upon re-entry are priorities that precede any walk on the surface. Ensuring that the infrastructure functions flawlessly is the true monumental leap of this decade, ensuring that when we land again, it will not be just a visit, but a permanent stay. Solving all the mysteries of the mission seems within reach, but one final detail about what the crew saw on the dark side remains hidden. There are reports and images from past missions that suggest unexplained presences and luminous phenomena in deep craters, fueling debates about what truly awaits us out there. What Reed, Victor, Christina, and Jeremy declare after landing could change our perception of Earth's place in the cosmos. The final word on this historic journey will not come from official statements, but from the physical reality of a capsule floating in the Pacific Ocean. The loop initiated at launch concludes when the main parachute opens, bringing humanity back to its starting point after a journey of thousands of kilometers. The final resolution reconciles the paradox between extreme danger and the need to explore, proving that we are capable of extraordinary feats. The engineering of the giant SLS and the Orion capsule confirms itself as the necessary life insurance to advance beyond low Earth orbit. The unification demonstrated by international cooperation during the mission seals the idea that space is the terrain where terrestrial borders lose their meaning. The success of Artemis II ensures that the next step will not be taken by a single country, but by a unified species that has decided to no longer limit itself to the soil of a single world. Your participation is crucial for maintaining scientific rigor and the debate surrounding these monumental advancements. Please share your opinion on space risks below. Following each stage of this mission is to witness history being written with fuel and courage, and your interaction helps strengthen the community of astronomy enthusiasts. We want to know if you believe that humanity is truly prepared for the isolation of Mars, or if the Moon still holds secrets that we are not ready to face. The safe return is a triumph, but the horizon now points to the hidden secrets of the lunar poles that Artemis III must uncover. The mission concludes with the certainty that Orion is a fortress against the uncertainties of the vacuum, but also with the awareness of our fragility. Every technical choice, however controversial it may have been behind the scenes, proved to be the path to transforming the impossible into routine. The real leap was ensuring that the return journey was as precise as the roar of the initial ignition, closing the exploration cycle that began more than half a century ago. Although Artemis II has returned, the data collected revealed a thermal anomaly at the lunar South Pole that no NASA scientist has been able to explain so far. What the sensors have detected beneath the eternal shadows of polar craters may be the most valuable resource in history, or the final warning that we are not alone in that grey rock.